Ladies and gentlemen, a warm welcome to another webinar of VCSEL imaging. This webinar is all about the latest camera of our fourth camera generation, the UltraCam Condor. That camera was announced in September of this year. The camera is a wide area, high altitude mapping system for a very specific application. My name is Alexander Wichert. I'm the CEO of VCSEL Imaging, and Bernhard, our application specialist, and myself, we will present you this camera system and how it interacts with our UltraMap software system. So my first part will be to give you a first introduction into the camera architecture, the camera design, and then in the second part, Bernhard will talk about how this interacts with our UltraMap workflow. What do you have to expect in this webinar? As I already mentioned, I will give a brief introduction into the fourth generation camera architecture. Then I'll talk about the specifics of the Condor camera, and then I will hand over to Bernhard, who gives the overview about UltraMap. And of course, we also talk about application, and all that is rounded up by a question and answer session. So if you have questions during the webinar, please be so kind and type your questions into the Q&A pane of the software system. The webinar itself, the presentation, has been pre-recorded for great user experience, but for the Q&A session, you will have us live and answering all the questions you might have. So I'm looking forward to talk to you later during this webinar again. With the UltraCam, we talk about camera generations. The first generation was introduced 2003 with the UltraCam D. The second camera generation was that famous UltraCam X Prime series, which we launched in 2006 and further evolved over a couple of years. Then the third camera generation, this is where we moved to all these birds of prey. We introduced the UltraCam Eagle in 2011. And common in all the generations is that we are doing a kind of revolutionary steps when we jump from one generation to the other. In between, these camera generations evolve with several facelifts, and now we are doing another big step, which is the step from the third camera generation to the fourth camera generation. The fourth camera generation consists now of two camera systems. The UltraCam Osprey, our oblique camera system, was the first one which we were implementing in the fourth camera generation. That was announced about almost 1.5 years ago in May 2020. And now this year in September at Intergeo, the second camera based on the fourth camera generation is the UltraCam Condor, which we announced exactly at Intergeo. Each camera generation consists of an underlying set of technology, and based on this set of technology, we are evolving one camera system and then the other one and then the next one. So when we talk about the latest, the fourth camera generation, one feature across all the cameras which are based on that is a CMOS-based imaging sensor. All former UltraCam have been based on CCD. Now we feel CMOS is in a right stage to be used also in area cameras, and that's why we have transformed all UltraCams, or why we are transforming all UltraCams into the latest CMOS technology. Together with that, there are a lot of new pieces. Literally for the fourth camera generation, we again touched every screw in the camera. So it's not only the imaging sensor who is new, we designed new electronic to deal with the higher throughput of the CMOS sensor, to deal with the higher image dynamic of the CMOS sensor. Then we also designed new lenses to resolve the higher resolution of the CMOS sensors. And all that together has a huge user advantage so that the cameras can be flown in even increased flight envelope when it comes to sun angle and overcast flights. Another common feature of the fourth camera generation is, thanks to the CMOS technology, a much faster frame rate. So we are now at 0.7 seconds frame rate, and that enables to either fly faster, or to collect imagery with a higher forward overlap, or do a mixture of both. Across all cameras, the footprint increased across the flight strip as well as along the flight strip. Together with this technology, the cameras became lighter, the footprint of the head became smaller, so we designed a new housing, although the power consumption is lower. So there are a lot of additional benefits which make the handling and the operation of these cameras easier. With the increasing footprint, that also means the data taken per capture increased, so we also implemented a new storage system. And also in the whole housing concept, we made the storage even easier to accessible, and also the IMU installation became easier. No calibration is, for example, recalibration is, for example, required. So we worked on a lot of fine details to improve that fourth camera generation, as I already mentioned, in literally every screw. However, as there is already an existing environment, the current environment, like an existing GPS INS system or an UltraNav system, can be used with the fourth camera generation like it was possible with the former camera generations. And of course, if you have a mount like an UltraMount 3000 or an UltraMount 4000, that can be used with the fourth camera generation too. For the data processing, the fourth generation, the Osprey and now the Condor is fully and transparent implemented into UltraMap, so that can consistently be used like you're also used to it from former UltraCams. There is one feature where we are especially proud about, and this is what we call adaptive motion compensation. In former technologies using CCD sensors, there was a forward motion compensation capability implemented on the imaging sensor that was forward motion compensation by time-delayed integration. We were always hoping that something like that will also be implemented on a CMOS sensor. That's, for whatever reason, not the case. And so we developed a completely new approach how to deal with motion blur in an image. We are now absolutely proud about and impressed by the results. We are now using in this adaptive motion compensation a software-based approach. So there is no longer charts shifted over a CCD, or there are no longer any sensors moved mechanically around, which adds all these uncertainties about whatever precision, accuracy, wear and tear. So we are now using a software-based approach to deal with the motion blur of an image. And the big advantage of this methodology is that it can not only correct the motion blur along track, like it was possible with time-delayed integration, or if you shift a sensor, like you moved the film many decades ago. The software-based approach is capable to deal with multi-directional motion blur. So, well, flight is clear, moves along, so that can be corrected, but if you have additional effects, when it was a rough flight and you have roll angles or so, and the mount couldn't compensate fast enough, then also this multi-angle motion blur can be precisely detected and corrected by our AMC methodology. That is totally unique and is especially important if you fly with oblique cameras, as here you have large residuals in your oblique images when there's a kind of a rough flight. So what you see here on these slides are examples about an imagery taken during a quite rough flight. So there are quite some residuals left in the motion blur, not only along track, but also due to roll angles. And it is fantastic to see, if you compare the two imagery, AMC switched off or on, how precisely and well this software corrects the motion blur, obviously visible in the imagery. Okay, after all this general introduction into features, into common features of the UltraCam 4th generation, Let's talk about the detail. So what I do have with me here is the Condor 4.1. That is exactly the camera which we introduced at Intergeo September this year. And as you can see here, it comes in a new shape with a new format and shape of the head. The colors represent this wide area mapping sensor. And I'll talk later about the housing, but at the end, this is what this webinar is about. The Condor is designed for what we call wide area mapping, usually taken at high altitudes. So it is a kind of an ortho robot machine. When your challenge is to map states, countries, continents, then this sensor is the sensor to go with. The footprint in the latest generation increased to more than 48,000 pixels across the flight strip. So that is an absolutely impressive flight strip for the utmost flying efficiency. And that combined with the legendary UltraCam image quality gives you the perfect tool if you want to generate ortho imagery over really large areas. But in the Condor, it is not only everything about the imagery. Beside the color imagery, that camera system collects also pen imagery, and that pen channel acts as a kind of a photogrammetric backbone. So it is possible, together with the UltraMap workflow, to generate 3D point clouds, DSM, DTMs, which then later is used to auto-rectify the imagery. So at the end, this sensor gives you all the data you need to generate ortho imagery. There is no additional LiDAR data set or LiDAR flight required. You can collect everything you need in one pass with the UltraCam Condor with the utmost flying efficiency of 48,000 pixels across the flight strip. To fulfill its task, the Condor has a very unique camera design. Usually in a photogrammetric camera, it is all about a high resolution pan channel and lower resolution color, and then you obtain your imagery by a pan sharpening process. The Condor is somehow the other way around. The high resolution, the 48,000 pixels across the flight strip, are all in the RGB channel. Here we have a very rectangular, very wide, but not so long strip of RGB color, and that gives the full resolution of color information for the ortho imagery. In addition, we have a pen channel, which is of course covering the same width, but is much more extended also along the flight track. So when the camera fires, there is a huge forward overlap in the pen channel. The pen channel is designed only to be used as a photogrammetric backbone. So we are using the high forward overlapped pen channel to later generate point cloud DSM DTM that gives the 3D information we need so that we can overlay the RGB imagery and generate the ortho image. So it's a kind of a reverse concept of a photogrammetric camera to optimize for its intended application. That means ortho image generation with record flying efficiency. In addition to the RGB and the pen channel, the camera has a near-infrared channel in a lower resolution, which supports land classification. So that is also an application that you can do with the Condor. Thanks to the very fast frame rate of 0.7 seconds, that camera can be flown very, very fast and is designed to be operated in planes like turbojets or even jets. To deal with all these smaller pixel pitches of the CMOS sensors, all lenses have been designed newly and they are all temperature controlled. We have temperature measurements across a lens so that we can later also do a lot of corrections and modeling for the utmost sharpness and contrast and geometric stability. So in summary, the Condor combines a high-resolution RGB strip with more than 48,000 pixels across the flight strip, with a pen channel acting as the photogrammetric backbone, and all that is supported by a lower resolution near-infrared channel for the multispectral capability of the camera system. And as I already mentioned, adaptive motion compensation has been implemented as a feature of all fourth camera generation. So although each sub-image taken by the Condor is supported by the adaptive motion compensation, so the camera is fully capable of resolving multiple angle motion blur. When we look on the camera system, from the third generation to the fourth generation, the design of the camera changed. So we have a different shape of the camera head, which makes it easier to install the cameras in planes where the hole is not exactly centric in the airplane body. Then we have a kind of new handles which are easier to use. And then here also in the camera cylinder, we have implemented multiple mounting heights already here in the cylinder, which makes tools like a camera lifter obsolete. So a lot of fine details have also been changed here. The storage can be accessed from the top, the IMU can be accessed from the top. So that all together makes it easier to install and handle and operate the camera. As I already mentioned several times, the Condor is a quite specific camera system with a different system concept like a standard photogrammetric camera. So the intended applications are all about ortho image generation of wide areas. So if your task is mapping a region, a state, a country, a continent, in resolutions, I would say target resolutions of 10 to 30 centimeter, then the Condor is the camera system to go with. It has full multispectral capability. It has the capability to generate the required 3D data, so you can really just use this camera system and you don't need any other data sets or any other flights like a LiDAR flight and map your continent. So the Condor is the camera when it comes to a kind of base layer also image generation, a kind of a base mapping, or when you want to do classification over large areas, or when you want to do a kind of change detection over larger regions. Thanks to the high flying efficiency, it's affordable to use the sensor on a kind of an annual basis or whatever your intended rhythm is, map large regions and do a comparison year over year, something like that. Typical customer for the Condor are government agencies as well. On big continents, they need to deal with large regions. We have also scientific agencies who are very interested in Condor data sets. Also, large IT accounts are being served with Condor data, and also the insurance industry is heavily drawing on Condor imagery. So at the end of the day, whenever a data set, a high quality multispectral data set is required over large areas, the Condor is the camera system to go with. We by ourselves, Vexel, we are also drawing a lot on the Condor. The Condor together with the oblique camera system, the Osprey, these two cameras together are the cameras we are using for our own Vexel data program, and with the Osprey, with the oblique camera system, we are mapping the cities, and the Condor is used to map the countries and the continents. We started some years ago, and since then we are collecting data from coast to coast across the US. We are collecting data in Europe, we are collecting data in Asia Pacific, and for our Blue Sky program, which is our kind of a standard serial mapping initiative, the Condor is used for all these wide area mapping tasks. But the Condor has not only been used for our regular flying, it also showed its capability already a few years ago when there was this massive hurricane Michael, who was coming over Florida and the islands before, destroying a lot, destroying thousands of houses. We went into the air together with the Geospatial Insurance Consortium, and we mapped a large area of 85,000 square kilometers with the Condor in just 3 days. That is a kind of record mapping capability, and it helped immediately the first aiders, NOAA, FEMA, Red Cross, police, but also the insurance agencies to deal with the disaster scenario on the ground and help the people as fast as possible and as good as possible. So nowadays, hardware is nothing without software. So the camera collects the data in a raw format, and UltraMap is our processing software system which grabs the data and then processes it from the raw data into the user-specific formats. UltraMap by itself has a modular architecture, so it consists of several modules which you can take to fulfill the tasks you want to fulfill. It's based, or the philosophy is utmost automatization wherever possible to save for manual labor time. But on the other side, you can also interact at each step. So it's not a black box system. You can tune your parameters, you can define your parameters, and you can tune the outcome so that you achieve the results you want to achieve. And the software by itself has also tools which allow manual interaction. So whenever you feel it's necessary, or if you want to achieve a very specific result, UltraMap has all the tools so that you can do that. As we are now talking nowadays about huge amount of data, each image capture much more than 1 gigabyte projects of 10, 20, 30, 50,000 or even more imagery. It's all about a highly powerful processing. UltraMap has distributed processing embedded so you can scale your computer system and the software with the tasks you have at hand. The user interface is consistent and guides you through all the modules. So it is a highly intuitive software system. And not only each module is embedded in a consistent user interface, also if you need to deal with a project flown by several UltraCams, even from different types, that is all visualized in a very consistent way. And if you need help, we have the Vexel specialist is only an email or a phone call away. We have support centers in all major time zones across the world, and you can have a direct and easy access to world-class photogrammetric people. The first step after the data ingest is the UltraMap Essential module. Here all the geometric and radiometric calibrations are applied, and the raw data imagery is transformed into imagery based on JPEG, GeoTIFF, for example. From that step you can either go into third-party soft copy systems through standard interfaces, or you continue in the UltraMap workflow, so you can do the AT in the UltraMap workflow and also take it from there to somewhere else, or you do again the next step, which would be the dense matching. That gives you point cloud, DSM, DTM generation, and then you jump into the ortho pipeline where you then overlay the 3D data with the imagery that gets you the ortho imagery, either based on a DSM or in the DTM. And then last but not least, the final module, the last module of UltraMap would be the 3D tin, which generates you a 3D structure, a 3D tin. All these modules have standard interfaces for data export, so it's an open system. Whenever you want to export your data set to deal with application-specific software, that's easily possible. This brings me to the end of my part of this webinar. I'm now looking forward to hand over to Bernhard. Bernhard is our application specialist, and he will give you a detailed insight in how the Condor works together with UltraMap. And I see you later in the Q&A session. Thank you very much, and Bernhard, the floor is yours.
Yeah, hello everyone, and thanks for listening to this webinar. My name is Bernhard Schachinger, and I work in the Vexel office here in Graz, Austria. I would like to show you some data from the new Condor 4.1 and demonstrate some steps in the UltraMap workflow. We see here a small subset of one of our test flights with the new Condor over our test field in Gleisdorf near Graz in Austria. And this data here was captured with 15 centimeter GSD in RGB. That means 35 centimeter GSD in the panchromatic channel and 77 centimeter in the near infrared channel. The data was captured from a flight altitude of 4,900 meters above ground level. The blue symbols that we see here are the single shot positions of this flight. So let's have a look at the image types which are available for this camera, as the Condor has quite a special concept. So I switch here to the view images mode, and this allows to project single images down to a surface to see the image content in low resolution and to see the image overlap. So first let's have a look at the RGB. RGB is a very wide strip, but it is very short in-flight direction. So it has a spot width of 7.2 kilometer from this flight altitude, but in flight direction there is just very limited overlap. The overlap in flight direction typically is just enough to not have any gaps in the final auto product. Then next let's have a look at the panchromatic image. The panchromatic image has exactly the same width as the RGB, but in flight direction it is much bigger, so there is much more overlap for the panchromatic channel. This allows to do a very robust aerotremulation, and all further processing steps benefit from this high overlap, from this huge footprint which is covered by the panchromatic image. And then finally, switching to the near infrared channel, we see that this is almost exactly the same footprint as the panchromatic image. Let's have a look at these images in the 2D viewer. So I switch to the selection mode, select all the images and add to the 2D viewer. So now we are in the mode of the near infrared image, and when changing the size of the images as projected on the surface, we see that these images have very high overlap. The same applies also for the panchromatic image. And now switching to RGB, we see that there is this very narrow strip, but when changing to the full size in the display of the image, there is full coverage on the ground. So the RGB image has a very wide coverage sidewards, but very little coverage in flight direction. And this is for the benefit of being able to capture very high resolution at the great efficiency. The next steps in the workflow were then the import of post-processed GPS data and then importing some ground control points to be prepared for the aerial triangulation. The AT workflow starts with the automated extraction of type points, which are displayed here. So all of these type points were extracted automatically by the software and are color-coded here in this view to get an idea of the height of these points on the ground. We can view some measurement rays. So each of these lines is the connection of one photo center to the point on the ground. These type points are extracted from the panchromatic images. Therefore, they have this benefit of the huge image overlap. Then after the automated type point extraction, the measurement of ground control points was done. So these triangle symbols here are all the ground control points projected into the 3D view. And double click opens the measurement window for one of these points. So we can zoom in, do a measurement like this, and drag it to some position. The measurement window for the ground control points gives on the one hand an overview over all the images where this ground control point is visible, and on the other hand it allows to zoom into any of these images to full detail, to the full resolution. And then with using the arrow key on the keyboard, also this button here in the ribbon, the user can quickly jump from one image to the next to do all these measurements or to verify the measurements. So let's close the measurement window. And the next step after ground control point measurement would be to do a bundle adjustment. So this dialog window here allows to do some settings and apply parameters for the bundle adjustment. In this dialog window we see here also a new tool in UltraMap, which is the handling of templates. Templates allow for some dialog windows in UltraMap to store the settings and then load these settings for other projects. So this is extremely helpful when you have some data protection with always the same project parameters, and then you can repeatedly apply these project parameters to a number of production blocks. So on the one hand, this helps to reduce errors, and on the other hand, this speeds up the processing, as you do not need to worry about the settings for every production block after the next, which always follow the same pattern. The results of the bundle adjustment are summarized in a report or can be displayed as 3D vectors, as the residuals of components, or could be exported to some file formats. So like here the export for exterior orientation to some formats, or exporting of AT data, which includes much more than just the exterior orientation. So next step of the workflow is then to submit the automated color balancing. The color balancing tries to compare RGB values of overlapping images and make these RGB values of identical objects on the ground being equal, so that the overall image block has then an homogeneous look. The result of that adjustment is then combined to an orthomosaic, so that the user can easily see if there is any difference in between the single flight lines or in between the single images. Phenomena which can be compensated by this tool are things like different camera settings across images or flight lines, changes in atmospheric condition, changes in the light or date of time, to a limited extent, of course, so that seasonal changes cannot be modified, but some days typically can be handled by the color balancing. The typical workflow in UltraMap is that first the automated color balancing tries to find a homogeneous solution for the entire block, and then the user can do some fine-tuning of the color tones and the contrast and so on. So there are some tools available like the gamma correction, curves adjustment, or adjusting the levels. And this tool here, the local gradient correction, this allows to darken and brighten the data in a locally limited region, and that is applied of course not only to the orthomosaic here, but also of course to the single images in the background. After radiometric adjustment, the single images can be exported to TIFF or to JPEG, or the processing for a base layer can be started, which is a low resolution preview orthomosaic for the full data set. That serves then as the basis for selecting the tiles to process to full resolution. The software is flexible with what you want to process, so you can select just a few single tiles of your region of interest to process to full resolution, or you can select all of the project area to process. Of course, this heavy processing is taking advantage of the distributed processing being integrated in UltraMap, which means that a number of processing servers can be connected to one system so that the load is distributed automatically to all these processors being available. Typical data products to process for the Condor are the DSM, the DTM, and the DTM orthophoto. So now the base layer is loading, so in low resolution we have the overview, and now for the region where we have zoomed in we can display the DSM, the DTM, which was automatically derived from the DSM, and then the DTM based orthophoto, which was also created automatically. This orthophoto is available in RGB mode and also in colored infrared mode. So throughout the entire UltraMap workflow, we always have the near infrared channel available so that all the processing is done in a consistent way for RGB and near infrared. So at the end, when exporting the data, the user can decide if going for 3-band RGB or colored infrared or the 4-band RGBI. Let's take a closer look at the geometric information which is derived from this data. So here we have the DSM, which is processed by automated dense image matching from the panchromatic images. So in this case here from 35 centimeter ground sampling distance. From this DSM, the software is deriving automatically a DTM, a terrain model. And to better understand that, we have here a difference mask which shows all the objects which were eliminated from the DSM. So this processing of DTM from the DSM works with taking advantage of automated image classification. So using RGB and near infrared, the software tries to identify buildings, vegetation, bridges, and so on, and then is eliminating all these elevated objects from the DSM. So in that way, the software is then able to clean the DSM so that there are just pixels of bare earth remaining, and then fill these holes to make a flat terrain possible. This part of the project area shows a little bit more movement in the terrain as the flat city center where we have been before. The software tries also to identify automatically bridges and then maintain these bridges in the DTM. The bridges can be optionally activated or deactivated to be included in the DTM. The reason for that is if you want to do orthophoto production, then it is beneficial for the output quality of the orthomosaic to have the bridges included in the DTM. If you want to use the data for some other application, then you probably want to exclude the bridges from the DTM. In case that there are some issues with the DTM or the DSM, then UltraMap offers an integrated editor for the height fields. So this can be activated with selecting tiles, which should be edited, and then edit height field. And this opens the editor, which has both the DSM and the DTM, as well as there is even an overlay with the DTM orthophoto. There's also the non-ground mask, so all these objects which are being removed from the DTM available to make editing easily possible. This tool can be used for doing modifications of the DSM. So for example, this little building here can be removed, or we can remove the cars and trees and other objects here on the road surface. So this was before the edit, and this is after the edit. On the DTM, you sometimes might want to do not to remove some objects, but bring some objects back into the DTM. So this helps sometimes to improve the projection surface for the orthophoto. So in this case, just for the demonstration of this tool, let's bring back this building with the round top here into the DTM. So I select this region. Now I switch off the ortho overlay so that we see the DTM, and that was before the edit, that is after the edit. So with that tool you can easily modify both the DSM and the DTM, and then based on the new geometry reprocess the orthophoto. The orthophoto is created by automatically placing seam lines. The seam line algorithm is using all kind of input data which is available, so that's the DSM, the DTM, RGB and near infrared information, and with that information it tries to find a path through the AOI which avoids cutting through any objects and tries to follow roads, buildings, vegetation as good as possible. The seam line can be modified with using the seam line editor tool. So for example here we can use this tool to make this house and garden come from the red input image and not from this greenish one. So as I started clicking the polygon here in the red input image area, this is the default image, the new image being used for texturing this polygon. But in this window here, I could also select some other input images to texture the orthomosaic for this region. So let's use this one here and apply. So instantly this seam line edit is applied. It is processed locally on my machine here, and the display will be updated, and we have here now a new contribution mask for our orthomosaic, and not only that, we have also the new orthophoto available. So that was a brief overview of the workflow in UltraMap with the data from the new Condor 4.1. At this point in the workflow, you can export, of course, all the data to formats being well usable in other software, in other workflows. And with that, I hand back over to Alexander. Thank you.
Thank you very much, Bernhard, for this detailed insight into how the Condor interacts with UltraMap. Ladies and gentlemen, this brings us now to the end of our part of the webinar, and I am happy to open the question and answer session. If not already done, please be so kind and type your questions into the Q&A pane of the software. Bernhard and myself, we are sitting behind our computers and are looking forward reading your questions and are looking forward to answer all of them. Thank you very much. Hi everybody, great seeing you, well, great talking to you in person at least, not seeing you. So Bernhard and myself are now behind our screens. I do hope that you liked our pre-recorded session on the UltraCam Condor. And now please be so kind, there is a Q&A pane of the software. Type your questions into the pane and we are happy to answer it. There's already a first question coming in. Can stereo compilation be performed from the imagery such as DOT applications? Also, what speed and altitude could you acquire 3-inch or 7.5 centimeter imagery from? Bernhard, may I hand that question over to you?
Yes, so for the first part of this question regarding stereo compilation, due to the camera concept of the Condor, there are some limitations to the stereo capability. So the panchromatic image channel has a very high overlap, and therefore this would be usable for doing any stereo, creating stereo models, doing measurements in stereo, but this has the limitation of the low resolution. The RGB channel, in contrast, has the high image resolution, but quite limited image overlap. Limited means that if flying with typical parameters for a production flight with Condor, let's say 85% forward overlap with the panchromatic channel, then that results in about 20% overlap in RGB. And this is not very much for doing stereo measurements. So regarding the other part about speed and altitude, to capture 3-inch, so 7.5 centimeter imagery, so regarding speed, well, the camera is quite flexible with the speed you can operate it. As we have heard, the forward motion compensation is done by a software-based approach, not only compensating forward motion, but also motion of the camera, of the platform around other axis. And regarding speed, it's quite capable. So you can fly there quite fast. So 200 knots and more should definitely be within the range of the system to handle. So for the limit, we would need to calculate some details. And flight altitude, that's about 2,450 meters.
Thank you, Bernhard. Great. Next question is, what are the differences in the software workflow when using a Condor Mark 1 versus Condor 4.1? My assumption would be none, but Bernhard, please clarify the details.
Yes, absolutely correct. So there is no difference in the processing workflow. So the operator can work with data from both cameras without any additional need for training.
Great. So what is the overlap in the RGB channel? Forward overlap is in the range of 10 to 20%, preferable 20, and side lap depends on your flight parameters. It's literally similar side lab like an near infrared and pan channel, as they are covering the same size across the flight strip. Bernhard, am I right?
Yeah.
Great. All right. So I want to know how much this camera costs. Thanks and greetings from Argentina. Greetings back to Argentina. Depends, of course, a lot on the options and the details. So it roughly 850, 900K really depends on the options. So please be so kind and talk to your sales representative for a detailed quote. Can UltraMap perform AT and also generation for non-VCSEL sensor data? The answer for the time being is no. UltraMap is tied to UltraCam data. They are a solution, an integrated solution of the camera hardware and the processing software. We are internally talking about implementing kind of an import interface so that our non-VCSEL sensors could work with UltraMap, but that has not been decided yet. So for the time being, UltraMap can only process UltraCam data. Same question, does UltraMap work with imagery taken from other cameras? For the time being, the answer is no, it can't. It's tied to UltraCam data, and it's an ongoing discussion inside VCSEL if you should open UltraMap or not. Next question is, what methods would you suggest to preserve accuracy of areas in high relief for DTM also, so that peaks and valleys aren't rounded? Bernhard, may I hand that question over to you?
Yeah, so our automated approach is based on the one hand on doing some LCC, land cover classification, and on the other hand doing some analysis of gradients. Steepness of the terrain is being analyzed. So both of that goes into the decision of what is ground, what is non-ground. That is then filtered, and this is the way how we create the DTM. So the quality of the DTM reconstruction depends on a number of factors, and we constantly try to improve the algorithms which are doing that. And so on the one hand, we are working on this automated procedure to better support the DTM. And on the other hand, we do have the editor, which I showed briefly. And this editor allows to modify both the DSM and the DTM, and also like peaks or valleys to copy them directly from the DSM to the DTM. So it depends very much on the particular situation that you want to handle for what is the best approach to do so.
Perfect. Thank you, Bernhard. Next question is, is it possible to produce true orthophotos?
Yes, technically it is possible to create true orthophotos from Condor data. Also here it depends very much on the terrain and land cover. If the quality of the result will be acceptable or might have some limitations. The reason for that is because due to the image format of RGB and the overlap that with RGB is possible, there might be some occlusions around objects like buildings. So that means there might be some areas on the ground around elevated objects which are not visible in enough input images to fully texture the ground pixel in the orthomosaic. So that might lead to some artifacts in the true orthophoto.
Thank you, Bernhard. Next is not a question, but a comment on how we use overlap in our presentation. So thank you very much for this. The suggestion is that we should talk about forward overlap and side lap and not just use overlap to make clear which of the two we are talking about. Thank you very much for that comment. We are certainly taking that into account for our next presentations. How many pixels are in the long track direction of RGB? So the long track direction has 6,150 pixels along track. So it's a bit more than 48,000 wide, and it is 6,150 along the track. Can we use other drone data product with the UltraMap software? Not exactly clear what drone data product mean. So clearly UltraMap processes UltraCam data only. And at each processing step, UltraMap has interfaces so that so UltraMap can export the data in standard file formats. And then, of course, this data can be used for whatever software package. So that is possible. So you can start processing data in UltraMap and then export it to other softwares. But the other way around, that data from other cameras is used to be processed in UltraMap. That's not possible for the time being. How to get sample data? We have sample data available on our FTP server, so please be so kind and contact your sales rep or contact the VexCell support, and we are happy to guide you to the FTP server so that we see some more questions coming in. What enhancements are expected in this next software release? Bernhard, can you talk to that?
Yeah, so the upcoming release will have a few enhancements. Of course, supporting the new camera. And we are working on some user interface things like extending the theming to allow even more automatization in the workflow. And we are also working on refining the DTM algorithms. So what we have discussed before, there's also some improvement to expect. And yeah, these I would say are the main features for the new release.
Yeah. And in general, just to add, UltraMap is since its existence and continues to be an investment area of us. So we are very focused on developing UltraMap further and adding cool new features for the benefit of our customers. Next question is XP model is discontinued. Well, yes and no. So it continues to be supported by UltraMap, but there is a discontinuation about the hardware support in the near future. But you can always benefit from your UltraMap versions for quite a while. Is the software cloud-based? I would say it isn't, but Bernhard, you could elaborate more in detail about that. Right.
Well, the software can run in the cloud. It is not, let's say, not yet fully optimized and prepared for cloud processing. But if cloud computers are prepared in a way to act like their physical counterparts would do, then this would work. There is still the need to attach somewhere the licensed dongle via USB, but all that can be handled. So yes, it would work in the cloud as well.
Okay, good. Thank you very much for correcting my statement. Good. Is there a limit how much motion compensation, how much the motion compensation can account for? So here it is all about the adaptive motion compensation and any limitations to it. Bernhard, do you have any figures on what we could state here?
Yeah, so there is definitely a limit. So the limit could be, on the one hand, the speed of the aircraft, so speed over ground, or on the other hand, limit could also be the rotation of the aircraft due to turbulences. So yeah, there are some limits. There are methods to calculate that. The limits are in a way that flying with very high speed is supported. So like I said before, like 200 or 250 knots. So all that is possible. And for the limits, this would require some calculation, of course, for some scenario for project parameters to say what is there the limit that it cannot compensate the motion anymore.
Yeah. But is it, Bernhard, is it fair to state that the limits are so wide that there is literally no restriction of AMC to the survey flight? So it can really correct for what you see in areas or with respect to speed and motion blurs.
Yes, definitely. So the speed which would be able to be handled by the AMC, this speed would typically not be flown in the production scenarios. Typically, you would fly at a slower speed.
Yeah, yeah. So next question, is the purchase of an annual license required? So that's, I assume that that comes in regard to UltraMap. So that depends a bit. So we are offering several license models. One possibility is to do a one-time purchase of the software. And if you are not interested in a maintenance contract, then you can just buy it once and work with it. So in this case, there is no annual fee required. If you want to always have the latest and greatest software, you can add a maintenance contract to it. Then that is then based on an annual fee. And if you have signed in for the software maintenance, that is with that annual fee, you're always getting the upgrades of the software for free. So that is one package, let's say purchase plus optional maintenance. And then we are also offering a subscription-based module. This gives you higher flexibility in signing in and out for modules or signing in and out for additional cores. If you have a kind of a peak processing need, you can add cores. If then later you don't need them anymore, you can sign off. So that comes with monthly fees, which are calculated on the amount of software you have subscribed for this given month. So we have quite flexible licensing models to adjust to the need of our customers' business. You refer to a vertical camera and an oblique camera. What are the differences between the two? So that statement refers to the UltraCam Osprey. That is our oblique camera. And the Osprey has a kind of what we call a vertical camera. These are nadir-looking camera cones, which are collecting high resolution PAN. They're collecting near infrared and RGB. This is, I would say, the vertical part of the vertical camera of the UltraCam Osprey, designed for photogrammetric applications. And in addition, the Osprey has tilted cones and left, right, forward, backward, and is collecting oblique imagery, RGB imagery, in addition to the vertical cones. And that is what we call a kind of an oblique camera, which is also embedded. So the UltraCam Osprey combines two cameras, a vertical photogrammetric grade camera and additional oblique cones for oblique image capture. Next question. It's possible to remove all car object and count it from the ground, from the ortho image. Bernhard, may I hand that question over to you?
Yeah, so in the DSM, cars and other objects which are not moving will be included, as the DSM is showing the surface for the time of capturing the data. However, for the DTM, the software tries to find cars and other objects, and then these are eliminated so that we get the bare earth. So yes, we can answer this with for the DTM. we try to remove cars.
Perfect. Are slides available for educational purposes concerning the UltraCam Condor camera? So first of all, this webinar has been recorded, so a record of that is available, and the link will be sent out after the webinar. That's one possibility. If you would like to get it in a different format for your educational purposes, please write us an email, drop us an email, and we are happy to talk what you need and how we can help you. We have online training for UltraMap. So we do online training for UltraMap, especially nowadays with restricted traveling due to COVID. We have done a lot of online training to our customers for UltraMap, but this is not a kind of a standard package that we do it in a very individual way. So this means we talk to if a customer has a need, the customer and our support team, they talk together, and then we put a training scheme together and run it on an individual basis. Next question, can we produce the near infrared and the RGB image during the same flight path? So shall we understand that there is punch sharpening of near infrared channel against RGB resolution? Bernhard, please be so kind and work on that.
Yeah, the single image bands, so RGB, panchromatic, and near image, can be exported with their native resolution, of course. So as the camera is capturing the data, you can also export the data. And then UltraMap also offers to do this like pan sharpening to bring the near infrared channel to the RGB resolution. Of course, this is only possible to do for this area where RGB and near infrared overlap. So from one exposure event of the camera, there will then be for the extent of the RGB image, the RGB-I image available at the high resolution of RGB. So this is like pan sharpening.
Thank you. So I would say we potentially understand that pan sharpening refers to spectral area of pan. Not sure, Bernhard, has that already been answered with your last statement?
Yeah, I would say that belongs to the question from above. So yeah. Of course, using the RGB, that is not pan sharpening. This is like RGB sharpening. So yeah, this Correct. Needs to be handled, of course. But yeah, that is related.
Great, perfect. Thank you. All right. Thanks a lot again for that great set of additional questions. So there a few questions came in via the chat. So this is this camera a sweep scanner? Is this camera to use as LiDAR in area laser scanner? No, that is so that camera has nothing to do with LiDAR. It is an independent camera system, high resolution, high quality camera system for nationwide mapping. So that's a frame camera from the underlying concept, all based on frames. Well, it cannot be used as an aerial laser scanner. If you wish, you can fly it in combination with an aerial laser scanner, but in our understanding, that's not exactly necessary because the camera is collecting all data like the high-res pan for the terrain model and the near-infrared data by its own. UltraCam X and X Prime had some problems with stitching the panchromatic imagery correctly, especially in snowy and glacier areas, as well as large areas we see in shoreline. So that is true that in former camera/UltraMap generations, when the terrain was very uniform, there were issues in the precise stitching. This has now been resolved. We introduced many years ago already a methodology called monolithic stitching, which resolved the stitching issues in areas where the imagery showed very uniform non-structured terrain. So that has been resolved since many years. Do you need to own a camera to have a license on UltraMap? This is not necessary. Everybody can buy an UltraMap license, independent from owning an UltraCam. Having said this, for the time being, UltraMap processes only UltraCam imagery. So there is a link between an UltraCam and UltraMap. UltraMap does not allow to process third-party camera imagery. Next question is, on the color balancing workflow in UltraMap Studio, is it possible to run corrections in the ortho mosaic after the correction of single images? Bernhard would love to hand this question over to you.
Yeah, so in the color balancing workflow, we follow this approach that first there should be the adjustment. First there is the automated adjustment of the full image block. That means the software is processing automatically a low resolution DSM, and based on that, a low resolution orthophoto, and then this orthophoto, this orthomosaic is balanced, and the result of the balancing is shown directly on this orthomosaic. The reason for that is that only when having the orthomosaic, you can really see if images are well aligned to each other. And then in the next, so based on this orthophoto, you can do some manual adjustments of radiometry, which is applied in the background to all of the single images. And then in the next step, you could switch to a mode for radiometric adjustment of the single images. So where you then can see the single images, not in the orthomosaic, but all the single images, and fine tune each of these images in an individual way. So that is the approach. First the block adjustment and then single image adjustment.
Perfect, Bernhard. Thank you very much for this explanation. Can stereo be done with the Condor? Easy answer to that. No, that's not possible. The overlap along track is not big enough in the high resolution RGB channel, so the Condor is not exactly designed to do stereo. Bernhard, am I correct on this?
Yes, so theoretically you could do some stereo measurements, of course, in the panchromatic image where there is the high image overlap. But the panchromatic image has the low resolution. So in the high resolution RGB, the overlap is just, well, not feasible to do measurements in stereo. Therefore, in practical use, this camera is not the preferred tool for doing stereo measurements because of this concept, which is fine-tuned to some other use case.
Perfect. Yeah, thank you. So next question is, how many physical sensors are collecting the individual channels? So when we look on the color near infrared channel of the Condor, this is collected by one sensor. The pan channel is also collected by one sensor, and then we have the high resolution RGB channel, which is corrected by 5 sensors. And just double checking with Bernhard that it's correct what I have said.
Yeah, yeah.
Great, thank you. What are typical flight parameters for collection with the new Condor in your data program? Bernhard, do you want to take that?
Yeah, so right now we are collecting data there with 15 centimeter ground sampling distance in RGB, and at an overlap of 90% in flight direction and 30% sidewards. So these are the parameters for the collection with the new Condor.
Did you mention the flight altitude? There was a cut in the audio.
Flight altitude for 15 centimeter, that is about 4,900 meter above ground.
Thank you. Thank you. Which camera will you recommend for stereo measurements? So we have two cameras which are designed for stereo. One is the photogrammetric flagship, the UltraCam Eagle. That camera is perfectly designed to do all kinds of photogrammetric applications, including stereo measurement. And the second camera is the UltraCam Osprey. That is our oblique camera system, but in the nadir channel, it is a full photogrammetric camera, including high resolution pan. So although the UltraCam Osprey would be perfectly designed for stereo, and it has in addition the oblique capture capability, which is heavily used to map cities. So UltraCam Eagle, and if oblique is required, the UltraCam Osprey would be the two sensors we recommend for stereo measurements. What is the image overlap along track for RGB? Bernhard, that's in the range of 20%. Am I right on this?
Yeah. So we typically recommend to have a minimum of 85% overlap in the panchromatic channel in flight direction, and this gives an image overlap of about 20% in RGB. This is not much, as we have discussed before for stereo. This is not really sufficient. But for the orthomosaic creation, which is the main purpose of this camera system, this is perfectly fine. And this also gives some headroom in case of any turbulences.
Perfect. Thank you, Bernhard. All right, we don't see any more open questions in the Q&A pane. I want to just give a few more seconds to see if something comes in.
I see one more question here in the general chat.
Yeah.
So it is about, I assume you have atmospheric correction when flying almost 5,000 meter. Yes, so we have atmospheric correction on the one hand when running the aerotriangulation, when running the bundle adjustment. So we try to compensate there some of the effects. And on the other hand, for the color balancing, we also try to reduce the effects of the atmosphere. So especially from this flight altitude and with this very wide swath width, effects of the atmosphere have play a very big role in the imagery and in the orthomosaic. So this needs to have careful handling. So we try to take care of that as good as possible.
Yep. Excellent, great. Just looking on the Q&A pane. All right, good. Another question's coming in. Where can one get sample data? So we have sample data available for download. Please contact your sales representative or our support team, and then we are happy to get you the sample data. So I would like to thank you very much for attending the webinar. Also, thank you very much for the kind comments. I really do hope that you found it worthwhile to attend. Thank you very much for Claudia and Kati to prepare the webinar, and Bernhard to run this together with me. And thank you to the audience for listening. I really do hope to see you all in person soon again next year. Take care and stay healthy, and let's meet soon again in person. Bye-bye. Thank you.
Bye-bye.